Okay, so today you'll be learning about algorithms and computational complexity. An algorithm is, at its very core, a set of steps for solving a problem. Now, what kind of problem? Well, an algorithm can solve any old problem. For example, here we have an algorithm describing the steps to make friends. But generally, we'll only be talking about the algorithms whose steps can be performed by a computer. So, insertion sort and selection sort are two more examples of sorting algorithms that you're already familiar with. However, today we'll be talking in specific about algorithms that solve the traveling salesman problem. So, imagine you're a salesman and you're traveling to a bunch of cities. However, you want to take the shortest path possible between the cities. One thing you could do is feed the information about the distances between the cities to a program, an algorithm, which will automatically compute the shortest path that takes you to each city. To do this, we need to find a way to represent the cities and the distances between them in a Java program. So here we have a graph showing each city and their distances. From this graph, we can make a table with the number of the city on the top and side and the distances in the middle. This looks an awful lot like a TD array, so we write it thus in Java, so that the row and column numbers each correspond to a city. Now that we have a method of representing our problem in terms of Java code, we can represent a path, a solution, as an array of city numbers, like this. Our goal is to write a method to find the optimal solution, or shortest path, in an efficient manner. One option is to look through all possible paths and simply select the shortest one as shown here. Here's the code for that. Now here's a visualization of that code in action. So you may think that took a while, but imagine if we had one more city. Then there would be 5 times as many possible paths, and that little segment you just watched would be 5 times as long. If we had 20 cities, you'd be sitting here for around 15 times the age of the universe. This brings us to computational complexity, or why people don't brute force big things. To talk about how many steps an algorithm takes to solve a problem, we use something called big O notation. When n is the size of the input, we use big O notation to give a very rough approximation of how the length of a computation grows with n. In the traveling salesman problem, because the number of paths we have to check is equal to n factorial, where n is the number of cities, we say that the brute force algorithm for the traveling salesman problem is an O n factorial. This is very inefficient, and so are all of the other known algorithms that find exact solutions to the traveling salesman problem. Some of the fastest are an O2 to the nth, which is still fairly slow, and no one is sure if there are any algorithms that are faster. Further down, we see that sorting and searching algorithms tend to be much faster. Currently, the most important problem in theoretical computer science has to do with computational complexity. It is called P versus NP, and essentially asks if all of the problems whose solutions can be checked quickly can also be solved quickly. If you can solve it, then you should probably go collect your $1 million prize from the Clay Mathematics Institute. Although most computer scientists believe that P probably does not equal NP,
If they were proven equal, then there would be deep consequences. If checking a problem were to be equivalent to solving it, someone would argue, then what would be the value in creativity? This question and many others lie at the heart of computer science and reveals the relationship between thought and computation.